So thank you. Thank the organizers for the invitation. See you all have your cups of coffee. It's good. You're going to need it. And I want to start actually with this sketch. I have a gifted postdoc that I would like to challenge every now and then with different tasks. And I gave him this sketch, and I told him, oops, draw something about quantum processors, okay? And then he came up with this one, which is, I really like. This is just a sketch. The guy is a real artist. He will do like a painted version of this, but this is the first sketch, and I think it's already nice. And also, I think it kind of symbolizes and show how you can sometimes give your students something really cool that you have a feeling that it's going to work, and then they surprise you with the outcome. Okay, so this is us. This is the group. Here is Ivan and Jada. They are both postdocs working on quantum error mitigation. For some reason it's also okay. And however, in the group, we also work on quantum thermodynamics and on scalable diagnostics or benchmarking of quantum devices. However, again, the talk will be on quantum error mitigation. And just to get a feeling, I want to do kind of a short poll, and let's try, and guess how good are they. So this is an experiment I ran for demonstration on IBM Q. So it's a simple 3-qubit Fourier transform and the inverse transform. So the whole thing should perform as the identity. And then we measure at the end the overlap with the initial state, which is just 0, 0, 0. I also removed these swaps at the end just to reduce the level of noise. Okay? And any guesses what the answer is? Just throw random numbers and let's see. 85. 12. Okay. 26. Okay. 0.57. Okay. So that's average number. Sometimes it was lower, sometimes a bit higher. But the question is, would you trust the machine with a non-trivial computation? And this is not, by all means, a big fan of IBM. But the point is that there is need to do something in order to make this machine useful these days. So actually, NISC are somewhere in between. They are not good enough to be used as is, and also not big enough for error correction code. And one of the leading solutions is quantum error mitigation. However, they potentially have long-term impact, either in reducing the hardware overhead once error correction kicks in, and also because it doesn't rely on a specific representation or gate set. Some of the techniques can be applied to sensing, imaging, and more general systems. So before we go into that, let me do this differentiation between two different types of noise. One is coherent error, where essentially we want to implement one unitary, and the device implements a different unitary, but still a unitary. So for example, on the Bloch sphere, you see that we want to do a pi pulse, but we're doing a under rotation, okay, slightly less angle. But the point is that this is being done consistently, okay? So you can think about it as a miscalibration of the device. And the other type of errors are incoherent error, where essentially there is interaction with the environment, and as a result, in the subspace of computation, the evolution is non-unitary. And the way to deal with these two different noise are completely different. The leading solution for coherent error, other than constantly recalibrating, is to do randomized compiling. I will not go into it, but and the solution for handling noise is incoherent errors is quantum error mitigation. The point is that once applying randomized compiling, it actually turns the coherent error into incoherent error. Okay, so that's in the end what you get, and therefore, even if there is a perfect unitary with coherent error, after applying the randomized compiling, the outcome will be some Krauss map, some noisy channel, and then it's possible to address it with quantum error mitigation. Just a note that presently, there's no scalable way for measuring incoherent noise. I think it's a real problem. I mean, if you heard about some benchmarking techniques like randomized benchmarking, they're not really scalable. They're not done for more than 3 qubits. So I think this is a standing issue, and you can take a look at our efforts in this direction. What is quantum error mitigation? The idea is to make additional measurements on top of the, let's say, the expectation value we want to measure. And in these other measurements, we've tried to characterize the noise, and then by different means, cancel it and mitigate it. So it's a different philosophy from quantum error correction, and it's all being done post-mortem, if you wish, or post-processing. Now, most of the methods are not scalable. For example, probabilistic error cancellation and purification, nice methods, but not scalable. The one that it is scalable is, it's actually a family of techniques called zero noise extrapolation. And the most practical one is called global folding that I will present in one slide. For the remainder of the talk, I will ignore the possibility of coherent error, but this is because it's possible to do randomized compiling and to do this conversion. And indeed, in the experiments we do, we apply randomized compiling. So we can just, for the sake of the discussion, ignore them. So global folding, sorry, it's actually a nice idea. Let me illustrate it over a single CNOT. So let's say we have our gate or circuit, here's just a CNOT, and we measure the expectation value we're interested in. Then we do what is called folding, which are another copies of the circuit that creates the identity. And however, they have the same, if you wish, the same noise mechanism that appear in the original circuit. So since this is the identity, in the absence of the noise, we have the original circuit. But because there is noise, we are now increasing the noise, but keeping the unitary part the same. Okay, so that seems useless. But after repeating this several times and collecting the data, it's possible to put it on a graph. And for this first run, we just put it on the value of 1, because it's like 1 unit of noise. And then the second data point is 3, 5, 7, and so on. Now, the ideal value would be on this axis, because there's no zero. It's 0, there's no noise at all. So now the idea is it's actually quite nice to do extrapolation based on the data that we have towards 0. And you can see that it works better than just taking a 1. Of course, this is just artificial, but you can see how it works. And if we have additional point, we can do a better extrapolation using a higher order polynomial and so on. And more generally, there's actually an analytical expression for the coefficients, how we combine these different measurements. And you can see that it doesn't depend on how big the circuit is, or it's just something that you can store and use. There's no need to compute it. The problem is that in most cases, it doesn't work. Okay, there's one specific case where it works, but then you can do, if it's global depolarizing channel, it works, but then you can do other things which are much more efficient. So I'll show experimental results to show why this doesn't work, and also supported by analytical arguments. More than that, the performance limits are unknown. I mean, it seems like if we just add more measurements and have better high order polynomials to extrapolate, then we would get better accuracy, right? Or no? Who knows? So it's a bit heuristic, this method. Also, it's quite costly in terms of shots and runtime. And it's not just about, you know, having shorter queues and less waiting time. The problem is that most methods assume in one way or another that the noise parameter is fixed, that it doesn't change throughout the protocol. And if your protocol is longer, you're more susceptible to these variations, as one can see, for example, in this case, the T2 changes over time, the T1 changes even more. Okay, this is just randomly picked IBM data. Okay, now we'll present our approach. And the idea is that we we introduce a specific inverse, which you might think this is actually the most obvious way to generate an inverse of a channel. We just take the driving Hamiltonian, reverse it, and change all the amplitudes, the sign of all amplitudes, from minus to plus. Okay? In the absence of noise, this will generate, instead of U, it will generate U dagger, okay? The inverse. However, because there is noise, it's doing something else. And now what happens to the noise? We assume the following. This is actually not an independent assumption. It's something that follows from this, because imagine that you have your elements with different level of noise. When you reverse the drive, okay, so the noise will appear in a different place, okay? So it is reversed as well. For example, if there's in one qubit, there's a leakage noise because the driving is too fast, okay? There are non-adiabatic couplings to the third level. If we reverse the whole protocol, then this noise will happen at the end, okay? So it's as simple as that. And of course, if the noise is time independent, then it doesn't matter. And with these assumptions, we arrive to this formula, which is, we call it the kick formula or equation, which relate between the forward evolution, the noisy evolution, this inverse evolution, and the noiseless evolution. And the correction is of second order in the noise, which is often enough. And the problem is that this doesn't have a clear operational meaning, right? What is 1 over square root of something? But we can take this expression and transform it into a power series. And once we do that, then this has a clear operational meaning because it's just a sequence of operation that we can run. So the simplest way of doing this is to actually write add and subtract I, and then we can use the assumption that still the noise is not extremely strong, then KKI is close to the identity. Okay, so what's in the brackets is actually a small expression, and then we can do the Taylor expansion, and we truncate it. So this will be the first order mitigation, where this term is analogous to the folding that you've seen before. Okay, because we cannot do this in the same experiment. It's combined with alternating signs, so it really has to be, each term that you see here has to be carried out in a different experiment. And one can do this second order, third order, and it turns out that we get exactly the same coefficient as was obtained from this heuristic method with the polynomials, okay, which was a bit disappointing. Okay, we wanted to find something new, but what we learned about it is, I'll show the added value of using this kick formula. And more than that, we can go beyond this because we have some understanding of how the noise is actually being canceled. And that will be in 2 slides. But before, I want to show this crucial role of doing the correct inverse. Because one of the selling point, or so it really looks like an advantage, that in this global folding, you don't need pulse control. Okay? You just, if you have a C0, you essentially do another C0. If you have a swap, you do another swap, because these gates are the inverse of themselves. But this is exactly what you should not do. And here's a comparison between what happens if we run swap. So we have this 2 swap as a unit, okay? So that's the identity. And in the red curve, we just, instead of, as an inverse, we just ran these 2 swaps again. And you can see that it actually, it gets worse as we go to higher orders, and it really misses the target. However, if we use our method, you see that it saturates almost exactly to the exact value. There is tiny differences because of a slight error in the initial condition. Okay, it doesn't start exactly at the ground state, and also potential residual coherent error. But still, and it works consistently. I mean, here is just one data set, okay, but if you go to the others, you can see that it works consistently well over time. This is an example of what happens if the noise is a bit stronger, and you can see that it becomes more extreme. And this is our method, okay, with the proper inverse, okay, or the pulse inverse, and this is what is done in global folding. And I want to point out to this. This actually happened to me quite a few times, okay, that accidentally, okay, you get the right value. But it's important to go one order beyond that and show that it's essentially converged. Okay, so to me, this is a certain validity criteria that must be, should be followed in order to validate the correctness of the result. Good. So another thing we understand from the theory, which I haven't fully presented or at all, but I will a bit now, is that there is a saturation in the performance. Okay, there's no point in going to order 20 or 30, even analytically, because the way we get this kick formula is by writing the evolution operator as the ideal unitary times Magnus expansion, where this is essentially the dissipator, or the Lindbladian, if you wish, in the interaction picture. And we're keeping only this omega-1 term to get this formula. So obviously, at some point, the term we neglect, this omega-2, kicks in, and we stop seeing improvement. But as you can see from the scale, often this happens, I mean, after substantial attenuation of the error, and there are other reasons like coherent errors or time-dependent noise that limit the performance before that. However, just by, if you look on this picture with the extrapolation, it's not clear why there should be any saturation. Okay, so this was the low noise limit of our theory, but actually, if we know that the noise is substantial, there's no point in doing a Taylor expansion, where Taylor expansion is essentially centered around the value of, okay, so if we write the eigenvalues of ki is 1 minus x, so there's no point in extrapolating around 0 if we know that the noise is actually substantial, because we want to approximate the square root function in the whole interval where the noise exists, not just in 0. Okay? Sometimes there's nothing at 0. So here's an example of the difference between 1 over square root of 1 minus x, and this is what you get from the Taylor expansion, and you can see that, yes, of course, it works well at 0, but it quite quickly deviates substantially, while you can choose other polynomials that maybe they're not great at 0, but overall, they are better. Okay, so that's the main idea, and here's how it works in practice. So now we went all the way to 10 swaps. Okay, that's more significant noise. And the red curve is what we get from just this Taylor expansion. And the blue one is what we get from this expansion over the interval where the noise is. So essentially, getting better performance for the same order is always better. We can spend less shots and also do it in a shorter time and avoid the fluctuation or the deviation of the noise parameters. It's slightly more striking when we look on when we do simulation, where we can actually look on the eigenvalues of the evolution operator. And here, I think this is a 5-qubit example, okay, but the details are not that important. It more or less looks like this. So what you see here, this is the noise histogram, and this is the spectrum, or if you wish, the histogram of the unmitigated noise. Okay, and if we run just the first order Taylor, then we do increase the noise. We bring it closer to 0, okay, but not all the way in. However, if we do this strong noise, you see that it's quite nicely bring it to 0. This is just the first order, but if we do the second order, it will already not be visible in this plot. Okay, so to summarize this part, so if we compare these two methods, global folding use, and in fact, all the methods I've seen in the literature, which are similar to this, they use this circuit inverse, and we use the pulse inverse. Let me just comment that doing pulse inverse is not a big thing. I mean, it's a one-time effort. I mean, for example, Jadar, my postdoc, he actually wrote a code where you just put your gate in, and the output is this reverse gate. Okay? There's something called pulse gate in IBM that allows you to do this quite nicely. And we don't think anymore about the schedules, because it's automated. So from our theory, we can understand what is the saturation limit, and when time comes, and this will be the limiting factor, one can think how to cope with it. It was also not clear from the original paper whether one should do in these foldings first the inverse and then the circuit, or the other way around. And in fact, if it's a global depolarizing channel, you can show that it doesn't matter. But in all other cases, it does matter. And from the theory, we know what is the right direction. This is something that I cannot explain, something in the conversion to PowerPoint. But this theory is limited to weak noise, and we can go to weak, moderate, up to strong. The definition of strong is somewhat flexible, but let's say the survival probability when you go back and forth could be around 0.7. This is something we call strong. And another thing, we still have this assumption that the noise is just being reversed when we reverse the driving. But yes, it is possible that the parameters change in time. And we think we can handle this. We still haven't demonstrated this experimentally. But in principle, we don't need the noise to be stable for the whole experiment. We just need it to be stable when taking this set of folding, or we call them kicks. So for example, instead of, if we need 50K shots for the statistics, this would be one way of doing it. First doing 50K shots with no foldings, then 50K shots with one folding, and so on. But it's also possible to do just a limited number of shots for each kick and have more sets. And the fact that the noise changed from set to set, that doesn't matter. Okay, so. As for what next, the way we did this strong noise, we found this strong noise coefficients was essentially minimizing some L2 norm, and there's also a degree of freedom to choose the weight function, whether you give more weight to errors, to strong errors or to weak errors. So there's a lot to play with, and what we did was essentially the first thing that comes to mind. We're not claiming it's optimal, only that it's better than using the Taylor expansion. We think there's a room for improvement here. There's also degree of freedom how exactly you choose the window of extrapolation. Also here we're doing the simplest thing. It's challenging to go beyond this omega-1 to handle also omega-2, but we think it's an interesting challenge. Also, there are some, we think we can also better integrate randomized compiling with our method. They actually mesh together quite nicely, but there's room for improvement. And using the same tools, although it's not mitigation, but using the same tools, this Magnus expansion in the interaction picture and so on, we think that we can also exploit it to VQE in the presence of noise and get some better performance. And more than that, I think that this field will rise and fall on experimental demonstration and not just about a theory paper. And yeah, I think I'm done. I have one more slide, but I'll leave it to the question if there are. So.